power of 3 divided by 12 plus by 3200 multiplied by 35 minus 10, the whole thing squared. So I got 2.107, okay, can be 1.07 times 10 to the power 6 millimeter 4, or 2.107 times 10 to the power minus 6 meters 4. Okay, I'll do IZZ2 again. I'll do IZZ2 by just looking at the table. Okay, by just looking at the table. So IZZ2 is also equal to IZZ3. They have the same geometry. Okay, individual section is the same. So width is 20, depth is 80, cube over 12 plus by the cross-sectional area is 1600 multiplied by 35 minus by 60 squared. Okay, so 20 times by 80 power 3 divided by 12 plus by 1600 times by 35 minus 60 close bracket 12 is equal to 1.853 times 10 to the power 6 millimeter 4. Okay, so you can see a general pattern by just looking at the table, and I will do that now. Okay, so by just staring at the table, I just put the numbers just like that: 160, 20, 3200, 35, 10. And I've done a spreadsheet on this, okay, when I give you all your term test. Okay, so 20. The pattern is the same. 80. 1600. 35. And 60. Once you've done this, yeah, you don't do what the solution manual that's not done by me show you, okay? You make mistake easily. By this way, you don't make any mistake at all, okay? Or you minimize your mistake. Stavro, can you calculate again, okay? I'll do mine again. IZZ, was 160 multiplied by 20 power of 3 divided by 12 plus 3200 times by 35 minus 10 close bracket squared. I get 2.107 times 10 to the power minus 6. Okay. So now you can calculate your IZZ. So this is equal to IZZ1 plus by twice IZZ2. Okay. So this will be equal to 2.107 times 10 to the power minus 6 plus by twice 1.853 times 10 to the power minus 6, because it's in meters now. Okay, so you will get 2.107 power minus 6 plus by 2 times 1.853 power minus 6 is equal to 5.813 times 10 to the power minus 6. Okay, we are good. Okay, so next we are going to calculate the first moment of area at point A. Okay, we're going to calculate the first moment of area at point A. I'll let you guys finish copying first. Any question from anyone? Is it moment of inertia? Jia Chang, moment of inertia when things are moving. Okay, this is second moment of area, because we're interested in the area and how the load is distributed in the area. So both formulas are the same. Sometimes can be different, but their consents in carrying what they are doing, depending on the term, right, is different. Okay. Yes, someone has a question. Stavro, you okay? You are okay? Oh, you are the one that another person have question. Where are you? Let me see. Who has question? Oh, Stavro again. But Stavro, you okay? You put your hand down already, or you still waiting to ask the question? Let me look at the chat. Did we take the negative power of IZZ? So because it's in meters, I think I'm asking the right. I'm answering your right question, right? So this is 10 to the power minus 6 meter. Okay. The unit changes. Okay. Okay. So now we are going to look at. I'm going to copy this diagram again. Now we have to apply our rules. Okay. Okay. So now we are going to find the shear XY at point A. We're going to do point A first. Okay. So I'm going to go to our rule book. Then we're going to come here. I'm going to paste the rule book. Okay. So these are the rules. Okay. If you have to do a help sheet, okay, or today you have to remember anything, it is these rules that you have to remember. Okay, I make it compact for you. Okay, these 5 rules. The first 4 are the most commonly used. The 5th one is quite rare. Some cases you have to use it. Okay. So now we have found our Vy. We have found our IZZ. Okay. So the formula that we're going to use is equal to Vy over IZZ. Okay. QZ is what we don't know and divided by T. Let's do something simple. Okay. What is T? Is T at point A equal to 0.16 or is it equal to 0.20 meters or 0.02 meters? Right? Which one will you use? We usually, so at point A, right? You're right. Okay, at point A is at the intersection, right? We will use this value, right? We will use this value because it will generate higher what? Shear stress. Okay. No point, because at point A is shared between the flange and the web. Okay. No point finding a lower value. You are wasting time. Okay. Find the highest stress value. Okay. So next, we know, we are aware that we have our we are aware that the distance from here to here is 35 millimeter. Okay, we know that now. So we want to calculate the first moment of area. So the area that we're going to consider is this entire area over here. Okay. So what I tend to do, I still like to call this my width. And this geometry over here is still my depth. So Q about the z-axis is equal to A y bar. Okay. So the area is what? The area is width multiplied by depth multiplied by y bar. Okay. So let's do the width and depth first. So the width is equal to 160. Do it in millimeters. Okay. Or if you want to do in meters, I'm fine also. So it's 0.16, the width. The depth is 0.02. Okay. Now, what is the y bar? Okay, so the y bar is this. So we know that the distance from here to here, right? That is your y bar. Okay, that's your y bar. And another way of doing this is apply the formula that we have derived, right? Remember, we have c minus or c plus y divided by 2. You can do the same also. So to find y bar is, you know that can we do that? Wait. Yeah, no, you cannot do that because this is from the top. Okay, so anyway, to do this is not, so you want to find this distance now. Okay, so you know the distance from here to here, this is equal to 20 divided by 2, this is 10, right? So y bar is equal to 0.035 minus by 0.01. That is your y bar. Okay, why that is the case? Okay, if I zoom in, the distance from here to here is equal to 0.035. Okay, 0.035. The distance from here to here is 0.01. Okay, that's it. Okay, so from here we can calculate our first moment of area. So 0.035 minus 0.01 times by 0.02 times by 0.16 is equal to 80 times 10 to the power minus 6. That's square. Let me do it again. 0.035 minus by 0.01. Okay, times by 0.02 times by 0.16 is 80 times 10 to the power minus 6 meters squared. So now we have everything. Okay, so the shear xy at point A is equal, so our Vy is 90 times 10 to the power 3, right? Our Qz is 80 times 10 to the power minus 6, right? Divide by IZZ. So our IZZ, I forgot what is our IZZ. Let me look at our IZZ value. Our IZ is 5.813. 813 times 10 to the power minus 6. Right. Now the thickness. Okay. You look at point A, thickness, right? The thickness is share both sides. What do I mean? Okay. The thickness, you have to consider thickness over here and the thickness over here twice. Okay. Because when the shear flow come down, okay, now I'm going to construct the shear flow. This is where construction of shear flow. Not this one. Come on, Eugene. Let me copy and paste. Okay. So over here, this is your Vy. And then your Q will go both ways, your shear flow. Like liquid flow, right? If you have water coming from the top, it will go both ways, then it will come here. So this is your Q. Okay. So you can see there's left and there's right. So now you divide by 2, and then the thickness is 20 times 10 to the power minus 3. Okay, so this is because left and right. Okay, so over here you have 90 power 3 times by 80 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 20 power minus 3 is equal to 30.965 times 10 to the power 6 Pascal. Let me do it again. 90 power of 3 times by 80 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 30 power minus 3. 30.965 is correct. Okay, so that is the that is the shear flow at point A. Okay. Okay. Any questions so far?
Can you